Good day everyone, and welcome to the organic chemistry tutorial. Today we'll be looking at electronic concepts in organic compound. I remain your tutor, Abdulbasit. For several episodes we've been talking about organic compound, and we're looking at the structure of carbon and how they interact with other elements. So today we'll be looking at the electronic structure, electronic concept in organic compounds, and these are one of the properties that make carbon a very special element. Now, carbon, as we all know, have an atomic number of 6. So if you have to write carbon, we say carbon has an atomic number of 6. Now, if you write the electronic configuration of carbon, it means we'll be having 1s squared, 2s squared, 2p squared. This is the electronic configuration of carbon. And also, if you write the electron configuration, which involves the drawing of the shell, we are going to have something like this. 1, 2, 3, 4, 5, 6. Now I am drawing the shell so that you can see it more visibly. It is evident that the outermost electron in the carbon is what? 1, 2, 3, 4. So we say carbon contains 4 outermost electrons, and that is why we say carbon is a tetravalent element due to its ability to form 4 different bonding. But a closer look at the electronic configuration, you will find out that the outermost electrons are dispersed into different orbitals. 2 of the outermost electrons can be found in the s orbital and 2 are found in the p orbital. So for carbon to successfully bond with other elements, it has to actually mix. It is very difficult for an incoming atom to bond separately with 2 different orbitals, since the outermost electron, which is 4, is not found in the same orbital. It is what? Found in entirely different orbitals. If you compare other elements like fluorine with an atomic number of 9, you have 1s squared, 2s squared, 2p6, 3s1. You will also observe that the outermost electron in this case is also situated in 3 different orbitals, because the outermost electron in chlorine is what? 7. So you see 1 is in p orbital, 6 is in p orbital, and about 1 is in what? The 3s orbital. So all these conditions are what make it very difficult for carbon to actually bond so easily. So in electronic concept, we are going to be looking at hybridization, the concepts of pi and sigma bonds, as well as a bit of hydrogen bonding, and then electronic factors influencing bonding in organic compound, or let's just say factors influencing organic bonding. Organic bonding. So hybridization. Now I have been speaking that the outermost electron of carbon is 4, and carbon can form 4 different bonds. But these 4 electrons are not found in the same orbital. They are found in what? 2 different orbitals. 2 of them are found in the s orbital and 2 of them are found in the 2p orbital. So if you draw the electronic configuration, you'll be having something like this. So as we know, the s orbital can only have 1 subshell. The p orbital has what? 3 subshells. So we have to write it like this. Now these 3 subshells of the p orbital could be, we could call it 2px, 2py, and 2pz. So if you draw in 1s orbital, we have 2 electrons there. So we have electrons like this. In the 2s orbital, we have 2 electrons there. We have electrons like this. And in the 2p orbital, we have what? 2 electrons there. Now this is the normal electronic configuration of carbon, and hence this is called its ground state. Now for carbon to successfully bond, like I have said before, these 2 orbitals have to mix, because this 2 orbital contains its outermost electron, which are 4. So 1, 2, 3, 4. Now, the mixing of these 2 different orbitals to produce an entirely new orbital with the same energy and the same size is called hybridization. So we say hybridization is defined as the mixing of 2 or more different orbitals, because it could be s, p, d orbital. But as for hydrocarbons, we'll only be looking at the s and p orbital. So, but the standard definition is that hybridization is the mixing of 2 or more different orbitals to produce a new hybrid orbital with the same energy and the same size. So it is only after you have done this that carbon can successfully bond with other elements. Now, we are going to be looking at different types of hybridizations that we have. Like I've said before, we are limiting ourselves to hydrocarbons. That is what this, we are going to be looking at in introductory organic compounds. So, introductory organic chemistry rather. So for carbon, or for hydrocarbons, which is the bond between carbon and hydrogen, we could have three forms of hybridization. We have the sp3, sp2, and the sp. So I'm going to be discussing these three kinds of hybridization. First is the sp3 hybridization. So in sp3 hybridization, or in every hybridization, we already know that this is the initial electronic configuration of the carbon before mixing. So this is called the ground state. Now, as we know, these electrons or these two orbitals have to mix. Now, for these two orbitals to mix, the electrons in the s orbital have to acquire energy that is enough to liberate it and then to jump to the next orbital. And when this happens, the electronic configuration shifts from the ground state to the excited state. Now, since we are only concerned with the last two orbitals, which is 2s and 2p, we will not bother drawing the 1s orbital again. So, at excited state, one of the electrons found in the 2s orbital absorbs energy that is enough to liberate it from the 2s orbital and to jump into the next orbital, which is the 2p orbital. So when that happens, we are left with only one electron in the s orbital. And originally, in the 2p orbital, we have 2 electron. Now, this one electron from the 2s orbital has absorbed energy, and that energy is called its excitation energy. So when it gets this excitation energy, it liberates and it jumps to the next orbital, which is the 2p orbital. So it jumps to this, and you know the 2p orbitals could be or the p orbital generally could be p of x, py, and pz. Or they just put the 2 there. So it's going to liberate the electron from the 2s orbital to the 2pz orbital. At this case, we say that this is the excited state. Now, having excited the orbital, the next thing now is for the orbital to successfully mix with each other. So, what is going to happen is that these 2s orbital now, having lost one of its electrons to the 2p orbital, is going to be in harmony with the 2p orbital. So, they are going to successfully mix with each other and to form a new hybridized orbital. Now, the subshells are the same. We have 2 and 2 here, so neglect that. Now, at the s orbital, you write your s. How many electrons can be found there at excited state? We have only one electron there. So let's say we have S1. At your p orbital, which is the whole of this orbital, how many electrons can be found there? This is 1, 2, 3. And all these 3 electrons are mixing with the s orbital. So you write your p and you put the number of electrons you can find there at the top. Now, mathematically, s raised to the power is still s. So originally, s on its own means s raised to the power 1. So this is what is called sp3 hybridization. So you just know the steps, and in hybridization, excitation has to occur and then the mixing of the orbitals. So in this sp3 hybridization is actually common in alkanes. It's common in alkanes, that is saturated hydrocarbons. It's common in saturated hydrocarbons, which are alkanes, and it has a bond angle of, because hybridization is also necessary in determining the shape of the atom. So it has a bond angle of 109.28 degrees. And then it has tetrahedral shape. So let's take, for example, if we have methane. Now methane is CH4. So if we draw the structure, we are going to, let's say we have it like this. So C and 4 atoms of hydrogen. 4 atoms of hydrogen. This is methane molecule, right? So we could represent this, we could see that this is something representing a solid tetrahedral shape. Because if you trace down, we're going to have maybe something similar, something like this. So obviously this is something tetrahedral. And that is why the sp3 hybridized orbitals are said to be tetrahedral. And this is common in alkanes, like I have said earlier. Now, as for the sp2 hybridization, what actually happened is the same thing that happened in sp3 hybridization. That is, the electron gets excited and jumps to the 2pz orbital. However, the difference is at the mixing of the orbital. Now, during the mixing, at excited state, we are now going to be having something like this. Let's write it here. So at excited state, or let's start with ground state. At ground state, we still have the same thing. This is your 1s, 2p, and 2s rather, and then the 2p. It would be 2px, 2py, and then 2pz. Having done this, at the excited state, what happened? The one of the electron in the 2s orbital gets excited and jumps to the what? 2pz orbital. So don't let us waste time. Let's just write it like this. And this is what? Excited state. You know, this is obviously the same as what happened initially when we were doing the sp3 hybridization. Now the only difference is that the 2s orbital is not going to mix with all the 2p subshell. Rather, it is going to mix with what? Only 2. Which we have what? It's going to mix with what? 2px and what? 2py. So we have an unhybridized orbital. So we say that what? It has what? One unhybridized orbital, which is what? The 2pz. So obviously, if you follow what we did before, at S we have only one electron, that is S, and at P we have 1, 2 that are what? Hybridizing. So we have what? sp2, and then an extra unhybridized orbital. So the question that they could ask you is that during the sp2 hybridization, which of the orbiter is unhybridized? Obviously, that would be what? The 2pz orbital. Because it is not possible for, during hybridization, for the 2s orbital to jump 2px, 2py, and go and hybridize with 2pz. It has to hybridize in order of 2px, 2py, and then 2pz. So since we are talking about s2 hybridization, the last orbital or the last suborbital is what? Unhybridized. So we say that in sp2 hybridization, the 2pz orbital is what? Unhybridized. We only have two orbitals that are hybridized, which is what? 2px and what? 2py. And this results in what? sp2 hybridization. This is common in unsaturated hydrocarbon, particularly in alkenes. And alkenes are known with their what? Double bond. I think we've done a class on functional groups. So here, the bond angle is about 120 degrees. That is the bond angle, and therefore their shape is trigonal. They are trigonal in shape. They are trigonal in shape. So if I have a particular kind of alkene and a bond angle is 120 degrees, or your normal geometry, usually, let me just give an example that you can easily remember. In your normal geometry, if you have something like this, a straight line, angle in a straight line is what? 180 degrees. So you know if we divide the straight line into 4, we are going to have 90 degrees each, right? But we are having 120 degrees, and angle at the point is what? 360 degrees. So something is trigonal, that's still trigonal. Or if we divide 360 by 120, we are going to have what? 3 sides. So in an alkene molecule, the shape is going to look something like this. So which means that we are dividing this angle at a point into 3, and each of them is giving us what? 120 degrees. Remember, in tetrahedral, each of the angles is approximately what? 109.28 degrees. 109.28 degrees. So in trigonal, each of the angles is what? Exactly 120 degrees, which is like 360 divided by what? 2. Divided by 3. So by this, if you carefully trace out, you'll be forming the what? The trigonal shape. So this is how the alkene molecules look like, and that's because their hybridization is what? They are what? sp2 hybridized hydrocarbons. Now, lastly, we are going to be looking at the sp hybridization. So the sp hybridization is common in triple bond hydrocarbons, particularly the alkynes. So what happens here is that similar thing, after excitation of the electron in the 2s orbital, the 2s electron is going to mix with only one of the 2p electron, which is what? The 2px, leaving 2 orbitals to be what? Unhybridized. So at ground state, usually we have something like this. Remember, okay, this is for sp2, I already wrote that. So at ground state, we have something like this, right? This is at ground state, where we have our 1s, 2s, and then the 2p. We have 2px, 2py, then 2pz. So at excited state, like I've said, this absorbs electron and makes it to jump into this orbital. Now this is excitation, so this is what? Excited state. Now after the excitation, the 2s orbital is only going to mix with what? One of the 2p orbital, which is the first one for the 2px orbital. So this will give us s, we have one electron out, p we have what? Only one electron that is mixing. This is going to give us what? Sp hybridization. It means that in sp hybridization, what happens? These two orbitals or suborbitals are what? Unhybridized. We say these two suborbitals, that is the 2px and the 2py, are the 2pz, sorry, the 2py and the 2pz orbitals are what? Unhybridized. So the 2py and the 2pz suborbitals are what? Unhybridized. So the question then comes that during sp hybridization, the mixing of the electron or the mixing of the orbitals is only between, you say it is what? 2s and what? 2px. And here, the 2py and the 2pz orbitals are usually what? Unhybridized. Like I have said, this is common in alkynes. And alkynes are represented by the presence of what? Triple bond. So we say that both sp2 and sp3 sp hybridization are present in unsaturated hydrocarbon, while the sp3 is present in what? Saturated hydrocarbon. Now in sp2 hybridization, in sp hybridization, the bond angle is 180 degrees, making the shape to be what? Linear. You know, angle in a straight line is simply what? 180 degrees. So that's what? Linear. Let's take something like ethine and look at it. So ethine is going to give us like this. It's only one hydrogen. It's only one hydrogen. Of course, obviously, this is a what? A linear molecule. So this is all about hybridization. And you could be told to determine the hybridization of each carbon atom or each central atom in a particular given molecule. So what you just have to know is that the presence of triple bond indicates what? Sp hybridization. So here, this carbon here is what? Sp hybridized. This carbon here is also what? Sp hybridized. And the presence of double bond indicates what? Sp2 hybridization. While the presence of single bond or saturated carbon indicates what? Sp3 hybridization. However, you might get confused if you have a very complex compound and you are told to determine its hybridization. So what you are expected to do is to just use a general formula which I'm going to give you. So let's say we have this exercise. I hope I can clean this place now. So let's say we have this exercise. We are told to determine the hybridization of each carbon atom in this particular compound. So we are giving compound like, let's say CH2 double bond, CH, or let's say C, 1, 2, 3, 4, CH2, right? Or CH, and 4. Yeah. So we have something like this. And you are told to determine the hybridization of each carbon atom. So we are going to be looking at what is the hybridization of this carbon, this carbon, this carbon, and this carbon. If you come to this carbon, you say, okay, this carbon is having double bond, so it is sp2 hybridized. But when you come to this carbon, you say, this carbon is having double bond here and it's also having single bond here. So which of them am I going to use to determine its hybridization? So you are going to be a bit confused. And that is why we have a general formula, which is what? Sp raised to the power of n minus 1. So this is the general formula you could use to determine the hybridization of any carbon atom, where the n here is representing what? The number of atoms or number of molecules around the atom that you want to determine its hybridization. So practically, if you're having carbon like this now you are going to determine the number of atoms that are directly attached to carbon, and that will be your n, for you just substitute it into that equation. So now, in order not to confuse you, this carbon is having CH2, so it's just like this, 2 hydrogens, right? And then double bonds towards CH. So if you want to determine the number of what? Atoms or molecules that are directly attached to this carbon, forget about the bond. So this particular carbon, how many atoms are attached to it? You could see that this carbon has what? Hydrogen attached to it. It has another hydrogen attached to it. Forget about the bond, irrespective of if it's a single or double or triple. Just be looking at the atom or molecule that is attached to it. So we have an atom here, and a molecule attached to it here. Making how many in total? We have what? 3 in total, which means that n is equal to what? 3. So if we substitute 3 into this, you'll be having what? Sp raised to the power of 3 minus 1, which is what? Sp2. It means this particular carbon is what? Sp2 hybridized. So if you have something like this carbon as well, All you have to do is to determine the number of atoms that are attached to it. So if you look at this carbon now, at the back we have CH2 attached to it. CH2 as a whole is a molecule, right? That is 1. We have hydrogen attached to it, that's 2. And at the front we have carbon attached to it, that's 3 as well. Or in order not to confuse you, let's just bring down this particular carbon. So this carbon, this is it here. So behind it we have CH2, and then we have hydrogen, so we could just put the hydrogen here, and then in the front of it we have what? Carbon. So you can see this is what? 1, 2, 3 atoms that are attached to it. So if you substitute 3 into this equation, you are going to be having what? sp2 as well. So it means that this particular carbon is what? sp2 hybridized. As for this carbon, in the front of it we have what? 1 molecule, and in the back of it we have what? 1 molecule, which means we have what? 2 molecules attached to it. So if you substitute 2 into here, 2 minus 1 is what? 1. So which means this particular carbon is what? sp hybridized. And as for this carbon, we have what? Hydrogen attached to it, which is 1 atom, 1. And at the back we have carbon attached to it, which is what? 2. If we substitute 2 here, we have 2 minus 1, which means this carbon is also what? sp hybridized. So with the aid of this general formula, it is easier for you to determine the hybridization of each carbon or each central atom that is given in a particular compound. However, if the compound contains other elements like nitrogen, like oxygen, and we use the presence of a lone pair of electron to indicate the incomplete bonding. So if you do that, you'll be counting your N as both number of atoms